like a hackathon and then you fight your like future wife via confounders form.
Hey, I told you it was useful for something. Course has applications. All right, we'll get started. So last time we finished up talking about non-deterministic PDAs. We didn't finish, we were in the middle of it. But I should probably start with announcements. We have an important homework due on Wednesday. If you haven't had a chance to get started, I highly recommend it due to the complexity of that homework and the fact that even if you fully understand everything we've done so far, there are going to be a couple of those pumping lemmas that are quite challenging. And I would be happy to talk to you about them in my office and help you get started on them. I assume that about 80% of you are going to want that by the time you turn something in. So plan for that in advance. Due to the pacing that we are going at, I think there's probably another assignment that I can get out to you by Wednesday. We're reaching the point in the course though where we're probably going to start alternating between homeworks that are due every week and homeworks that are due every other week. Just because of the nature and sizes of these assignments. I really wanted that to be this assignment, and I found that we are just far enough behind that it didn't make sense. So if something is really crunching you with this assignment, I may be able to extend it for you by a day because it is not the exam week, but that's going to be next week. So that will be something that we'll need to consider with regards to the homework that's coming out. I will probably, for the homework that's released this week, be offering the same thing that I did last time, which is if you turn it in early, then I can get you or guarantee feedback early. And then beyond that will just be a queue of submissions until TA drops dead. Questions before we dive back in? All right, so we had done this last time. We had finished this, I believe. And we ended analyzing this diagram of a non-deterministic pushdown automata to refresh you. We said we were going to use the bottom of stack character 0. I kind of turned that into a Z because I prefer Z even in binary, because sometimes we will want 0s and 1s to both be stack characters for languages in this class. So having a 0 as a bottom of stack character when it is sometimes a stack character can get a little bit confusing. So my recommendation is just always to use the same bottom of stack character as a Z, something like that. Yeah.
I don't know if you're aware of this, but Canvas is down.
Yeah, I think I didn't hear about that this morning.
Oh.
So that is very annoying. Hopefully people know ways to reach out to me if needed to do something like attend remotely. If that is the case, you can always email me. I don't think there's been a day where I have not checked my email before coming into class, so I can make sure that you can attend remotely even if Canvas is down. Stupid Canvas. So then we decided that this shouldn't really have an acceptor. We needed one for the 0 case, but why are we accepting this single A? That didn't really make sense. But other than that, the transitions were triples. And those triples are the character that is read, what we pop off of the stack, and we push onto the stack from right to left. So if we're doing a no-op, it looks like it's the same character. You push and pop the same character, and it's the equivalent of a no-op. If there are more characters on the right-hand side than there were on the left-hand side, and the first one is the same, then it's a push. Otherwise, if the second one is a lambda, then it's pop. Were there any questions on this form of NPDA? Is everyone caught up enough with lecture recordings that we know what we're talking about? All right, so the other thing we can do then is, because this becomes a little bit more difficult, and especially the way we're going to be visualizing a lot of our NPDAs is going to become more difficult, it becomes useful to be able to describe them in a different way. So we introduced the concept of an instantaneous description to give us a sense of exactly where we are and how we're proceeding. So transition graphs are wonderful. They help us to visualize DFAs and NFAs, but it turns out to be less useful in a pushdown automata. We'll see this as we get to a problem where it's like most of them are 3-state problems where all of the work happens in the middle state and there are just 12 or so loops within that second state. So there's just transition, 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 transition between the state and itself, all just manipulating different input character, stack character pairs on that middle state. And that is very annoying. So this notation can be especially useful in those kinds of problems where there are 12 self edges in a particular state, which is really annoying. So it's going to be a triple of what we're going to call QWU, where Q is the state of the control unit. So this is just Q0, Q1, Q2. So Q tells us which state we are in. W tells us just the unread portion of the string. So starting with the current character we are on, what is the rest of the string? What is left after we read this? Then U is the bottom to top stack contents. We then use the concept of the turnstile symbol to give us the transition from one instantaneous description to the next. So this allows us to just talk about a walk through one of these, not just in terms of states, but in terms of the entirety of what's going on within the string, what's going on within the stack. It allows us to visualize everything that we need in a non-visual diagram, a logical diagram. So yes, here I suggest starting to use Z to represent that bottom of stack symbol. So let's get an example of an instantaneous. Let's start with an NPDA, and then we'll go into an instantaneous description, I think. So here's a language. The language is the number of A's in the string is equal to the number of B's in the string. Now note that this does not mention anything about the order of those. So A to the N, B to the N is a sublanguage. It's a subset of this language. But now we don't care about the order. We could have all the B's before all the A's. We could intermix and have A, B, A, B, A, B. We could have some A's, have a bunch of B's, and then have some more A's to equal it out, or anything else. So since pushdown automata always use stacks, think about how you might algorithmically solve this using a stack. That might help you to think about how to construct an NPDA for this. So I'll give you a few minutes to think about it and work on it. Feel free to work in groups. And we'll see what we come up with. Anyone had a moment of brilliance on how to proceed?
Well, wasn't here for the first lecture on this, so depending on how this actually works, I mean, my thought was you have two states, one state for if you have more A's than B's, one state if you have more B's than A's, then you keep track of how many more on the stack. That was my thought.
That's a really good thought. It turns out we don't need separate states for that, but the symbol that we use on the stack is going to be the equivalent of that state, or what would be that state in a regular language.
Yeah, because whatever the input symbol is, it's the opposite of what's on top of the stack. Then
Yes,
you remove it from the stack, and then if the stack is empty, you return back to the start condition, which is also a final state, where
Yeah.
it's even.
smart. I like it. An excellent moment of brilliance. So I think we need to have two different stack symbols. They represent the idea of so far, given the characters that we've parsed into the string, we've either seen more A's than B's, in which case that stack symbol that we use representing more A's than B's is what's on top of the stack. Otherwise, the stack symbol for more B's than A's is on top of the stack. Otherwise, if the bottom of stack character is on top of the stack, that means we've seen an equal number of A's and B's, including 0. So since that is where we start there, and then we start moving forward. As we see a character, is that character an A or a B? Is what's on the stack, seeing that we've seen more A's than B's or seen more B's than A's. And with that pair of information, the symbol we're looking at and the symbol that is on top of the stack, we can make a decision about what to do with the stack. But the real moment of brilliance is realizing we don't need more than one state to do all of this. All we're doing is manipulating the stack. So if we read an A, we look at the tops of the stack symbol. If we see a 0, we push another 0. If we see a 1, that means we've seen more B's than A's so far. That means we've seen another A. We should pop, subtracting 1 from the more B's than A's that we've seen so far. If we read a B, exactly the opposite. So converting this into an NPDA form, we're going to have a Q0, and then as we move from here to our main state, we said that Q0 is accepting because there are 0 of each. We need to figure out, okay, what is the first symbol that we're going to read? We're either going to read an A, see a Z on the stack, the bottom stack symbol, and then we want to push a 0, saying that we've seen one more A than we have B, or we read a B, see a bottom of stack character, and push that we've seen one more B than we have A. This gets us to the disgusting middle state, Q1, that has all of the transitions in it. So we're going to do all of our A transitions up top. I'm going to try to leave myself enough room for that. And we're going to have some B transitions on the bottom. I'm just going to kind of group them together that all stay within Q1. So from within Q1, if we see an A and there is a 0 on top of the stack, we want to add a 0, saying that we had seen more A's than B's. We see another A, so we've seen one more A than B's than we had seen before we saw this character. If there's a 1 on the stack, then we want to remove it. And if there is a Z on the stack, which is very possible at this stage, then we want to do exactly as we did before, put on the first 0. The exact opposite for B's. For a B, when we see a 1, if there's a 1 already on the stack, we want to push. So this represents the push, this represents the pop, and this represents the push on empty stack. So I guess this could be the push on non-empty. We see a B, there's a 0, then we remove it, and a B, when it's empty, we want to push the first one on. So that's exactly the same order as we had on the top. Push on non-empty, pop, push on empty. Question?
Shouldn't there be an arrow that will move the state from Q1 to Q0 when the stack is empty?
Yeah, so we need something that either goes back there or moves forward to some other kind of acceptance on Z. If we have Z, then we need the ability to go back to that. So the way that I'm going to do this is because it is non-deterministic, I'm actually going to make either a Q2 or you could have a lambda transition back to Q0. But for sake of seeing kind of the order of this, I'm gonna make an unnecessary accepting Q2. That is done as a lambda transition. So at the without consuming a character, we can on the bottom of stack character move to Q2. And this is making the assumption that we accept with the bottom of stack character on the stack. If we wanted to say that we want to remove the bottom of stack character before we accept these last D's, we just become lambda. And then there is nothing on the stack, which means we cannot do additional operations because there is no bottom of stack character anymore. But that would be what allows us to accept. So this is what a lot of NPDAs end up looking like, especially simpler ones that we'll cover in class, is there's some middle state where we do a bunch of stack operations and then we determine how do we start and how do we end. We will eventually find that there are reasons to split states in pushdown automata, but let's not worry about that until we see one. Does anyone have any questions on this construction? What anything means, the logic of how to construct it, or why this works? I think we should run through an example anyway.
Well, I mean, I guess so far to me, I'm not sure I quite understand how it's non-deterministic because it seems totally deterministic.
Yeah, it's pretty close, aside from this lambda allowing us to not consume an input character.
Well, but if you're still checking the stack, then it seems like you could write like a which case basically you're doing conditionals, right?
Yeah, this is deterministic by nature.
Okay.
There are some languages that are deterministic, but unlike with regular languages, there's actually a distinction between non-deterministic and deterministic context-free languages. This is an example of a deterministic context-free language, which makes it a little bit easier to write an NPDA for. But yeah, let's go through an example, because I think that will help people to see what's going on here. Someone give me an example of a string that is accepted by this language.
A, B, B, A.
A, B, B, A. I like it. The string and it's a band. All right, so we would start in Q0, and I'm going to draw an empty stack for the moment. We push on that bottom of stack character. We assume the bottom of stack character is already on stack. You don't have to push that on as part of the NPDA. We're just going to assume that we start already there. So we start with our character pointer at the first A. And we say, if we're reading an A, the bottom of stack character is a Z. So we're going to pop the Z, pushing the Z and a 0 when we do this. This reads past the A and moves us to Q1. Now we see a B and there is a 0 on the stack. So we are, in this case, see a B, 0 on the stack. And this tells us to pop it, pop the 0. We're replacing that 0, popping it and pushing nothing in its place. So that moves past the B and keeps us in Q1. From here, we see a B with a Z on the stack. That's this case. So we're going to push a 1 on top of the Z. We pop the Z, push a 1 from right to left. So here's the state of the stack. We loop back to Q1, we move past this B, we're on the A. So now we find that we are in the reading an A, one on top of the stack case. So this says move past that A, pop the one that's on the stack. And now that we have a Z on top of the stack, we can teleport to Q2 and accept. Note that we could have teleported to Q2 after the second character. That was an element of non-determinism here. When we have a Z on top of the stack, we can either read a character or not read a character. We chose to not read a character, or so we chose to read a character here and not read a character here. But note that if we had chosen not to read a character, we would have teleported to an accepting state, but since there's still a character to read, we fail. We can only accept if three things are true. If we've reached the end of the string, the stack is empty, and we're in an accepting state. So we had to be at this point before taking this transition had meaning that allowed us to accept. But since we have that empty stack or empty stack with just the bottom of stack character on it, then we accept. How are you doing? Questions about that? If we had just had ABB, then there would have been something on the stack. And that would be the case if for any string where there are more B's than A's or more A's than B's, either have some zeros on the stack or we'd have some ones on the stack. If we had something on the stack rather than nothing on the stack, we would not be in Q2 or in Q0. We'd have to be stuck in our non-accepting Q1 in some kind of loop. Anything else before it goes away? Maybe some thumbs. How are we feeling about this? Okay, somewhere between here-ish and here-ish. We will get a couple more examples of this in ways that I think will help, hopefully. If not, I am very around for office hours and starved for attention. All right. Yeah.
But transition to Q2, we're stopping because we're not seeing the bottom of the stack by condition, and not because you can't do nothing when there's something on the stack.
Right, we're stopping because, yeah, we're at the end of the
Condition.
string. Yeah, we kind of hit that three case condition where we're at the end of the string. Bottom of stack character, and we're in an accepting state. Which is what is necessary in order to accept. All right. Let's actually write some instantaneous description forms. I probably shouldn't have erased that already. Oops. Well, here's an answer for us anyway. Note that I technically also did not need my initial state, Q0. Because this was just doing what was already in Q1, just the first instance of it. So this is an even simpler form. So let's take this simpler form and see if we can write instantaneous descriptions for parsing BAAB, which is the exact opposite of ABBA.
Is that like the ABBA tribute band?
Yes. Yeah, Bab. Or Bab. Be great to have a parody band of ABBA, just goats.
Yeah.
Bab. Sheep.
I'm sure Sora AI can do that.
Every single song. Mamma mia.
Yeah. The dancing queen.
The things we do on Monday mornings.
Yeah. Okay.
This is a stand-up routine waiting to happen. I swear that's my failed career. If I hadn't gone into teaching, I would have gone into stand-up. I don't know if that would have gone as well.
I mean, you've already set a pretty high bar for yourself with your teaching capabilities, so.
That probably differs on a student by student basis.
Fair.
He's keeping himself humble.
When you have to, the day you have an ego as a teacher is the day you stop being effective. Or you turn into stew.
Or the strangest people.
Yeah. So remember that instantaneous descriptions have those three components. We have the state that we're currently in, we have the unread portion of the string so far, and we have, what was that third element? Yeah, the stack from bottom to top. So let's get you started with the first one. When we begin, we are in state Q0. The unread portion of the string is the entirety of the string. We haven't read anything yet. And the stack just has the bottom of stack character on it. We then use the turnstile, very long turnstile. And we use that to, all right, what is the next move that we make?
So it would be Q0, AAB, and then you would have a 1 and Z, or a Z and 1, right?
Yeah,
Okay.
so our stack reading from, yeah, it's from top to bottom. It should be the same as the one that we do here. I'm thinking of bottom to top being from right to left.
Mhm.
But yeah, this is the entirety of the stack contents. Once we've read the first B, we've seen one more B than we have A, one character in. So there should be one on the stack. And then we turnstile again and go to the next, which is, we're still in Q0.
Yeah.
You read another character.
AB, and then just Z.
And we read the A, we're still in Q0. We have a B left, and there's a 0 now in the stack. We read that B, but we don't hop over to QF yet. We're still in Q0. We have nothing left to read, so we represent that as just lambda. And we're back to being empty. But now we note that we can take that final transition, reading nothing from the input because there's nothing left to read. And since there is a Z, great, that puts us in QF. QF, nothing left to read. And this does tell us to put the Z back on the stack, which gives us kind of our accepting character or the accepting state that allows us to show that. So this is a very easy way to show a particular run through an NPDA in a way that allows us to verify that a particular string is in the language accepted by that state machine. Questions on instantaneous description form or how that maps to the transitions in the NPDA? Yeah,
Could the stack fit with C, we would just keep adding ones, one just keeps adding.
yeah, if we would have characters, if there were more A's than B's or more B's than A's, then it would be pushing and pushing and pushing and pushing. But since we're kind of alternating A, B, B, A, there's nothing, the stack doesn't get too long. Yeah, if we had a string that was a bunch of A's followed by a bunch of B's, we would build up a bunch of zeros on the stack and then take them all off. A good point. Any other questions? Looks like there's a half question. Maybe an office hours question. Yeah,
Kind of, are the, as it's written on there, does the semicolon mean that the two sides are like on each line?
separate, yeah, like there are 6 transitions defined by this one self edge.
Well, no, but what I mean is the one on the left related to the one on the right, or is that just a note?
No, it's a note saying that they're separate.
Okay, gotcha, I just wanted to make sure.
Yeah, well, they are kind of grouped in the sense that we have the pushes, we have the pops, and then we have the empty stack. Empty stack, push and pop,
Okay,
but kind of the empty stack pushes and the pops. Yeah,
So yeah, I missed spots on Friday, I haven't watched the lecture yet, but did we go over how to construct these?
yes. Yeah, there's an example of constructing one. It was the one that we talked about at the very beginning of class. Hopefully that wasn't too much of a spoiler.
I don't know, I think seeing this first one actually will make it easier.
Yeah. That's probably true. Go back, like, oh, this feels like review now. All right, anything else before this goes away? Okay. In case you haven't figured it out yet, if I ask that and then give you a few seconds and then turn around, it's better to raise your hand and not have formed your question yet than wait until it goes away and be like, oh, I did have a question, I was formulating it. Let me know, and then let me give you the time to formulate the question so that I don't have to answer your question on a blank whiteboard and then your question doesn't get answered, which is the worst case scenario. I do that. It's gonna come out at the time.
I mean, you can still kind of see the drawing if I get the glare just right. I can-
You can see why at some point it is. There's still a CYK up there. I can't see it, so what's especially funny is now I don't know whether you're just hallucinating it or not.
Some light.
If you get the reflection just right. Now, if you read that part of it.
All right.
Sitting here, why are his pluses so lost?
They're turnstiles. All right, so next one is to make an NPDA for our old friend WWR. Remember, this is another example of what we used in our pumping lemma. We showed that this was not regular, and we want to be able to show that maybe it's context-free. If it is context-free, we should be able to design an NPDA for it. So think about, as usual, I find this to be a very useful question when we tackle these kinds of problems. If you were determining or writing an algorithm for this and needing to parse it at a single pass from left to right, how would you do this? Algorithmically, that's going to be really challenging because how you would typically handle an even length palindrome is you would start from each end and move inward. But with an NPDA, you have to move from left to right in a single pass.
You know, so I did the whole homework question with this R in the corner notation, and then repeating the verse of it's so much nicer and less stressful.
Oops.
Yeah.
Sorry about that.
Redid that one.
You have to just constantly have a second state that doesn't know whether or not you're halfway through the word.
That's a very good idea. Use non-determinism.
Yeah.
At every character that could be where you haven't hit the middle yet, you can guess this is the middle and fork your process. Where one is going to take in the next character and say, is this part of the left-hand side? And another that's in another state saying, all right, let's try to match the characters starting from here for everything we've seen so far. This is where non-determinism becomes very useful.
page.
Yeah.
Turing machines.
Yeah.
Turing machine transitions. That's a fun time. Yeah. Like assembly plus plus.
Assembly in a world where you have infinite tables.
When you take C and then you go plus plus, you get object-oriented loveliness. When you take assembly and you go plus plus, you get Turing machines, and it's worse.
So just object oriented assembly then.
Yeah,
That's a horrifying thought.
isn't it? It would make it easier, probably.
I'm not so sure. Then again, my main experience with assembly has been 6502, so.
Yeah, it's been a hot minute since I've done anything with any assembly.
So is this a
version?
What's that?
That version.
It's an instructional set. Architecture.
So
That's
all under Johnny stack and this is less custom back.
Oh, nice.
So this will cover stack.
Yeah, I only studied x86 and MIPS in undergrad.
I've been meaning to learn x86, it's been on my to-do list.
No one uses x86 anymore. Everyone's on x64, as they should be, but
Well, I mean, X.
it's basically the same thing. Yeah. It's just the least readable, I swear.
Yeah, that's kind of the main thing.
Yeah.
So I'm not afraid of assembly, just x64.
Certainly I remember writing a calculator in x86 and undergrad. And that is when I learned that I didn't like assembly as much as I thought I did. I was a very logical person. I thought, wow, this is just logic at its core. Tried to write that calculator. Think, wow, I'm not as logical as I think I am. The day you realize you're not actually a computer and go home and write yourself to sleep.
Well, 60,002 is pretty simple, but that becomes a problem when it's so primitive that it's easy, but in order to do things, like, it doesn't even have native multiplication.
Yeah.
So you have to come up with your own algorithm to do that.
Rid of paper relatively critical, like fastest way to honest. Like it's only useful if your number is like just stupid long.
So we have to see the shit and then very.
Lancer. So Lambda goes to sleep.
I need so many like.
Bab's children, Lambda.
Yeah.
So, big character.
The Chiefs young, the Lambs.
This is over back. So this case, inside, we're calling this girl. Okay, got it. Should agree, so, because you have to, we were essentially just, you have to have. This is all, whatever is your power pump. Yes. This, basically.
Is it legal to just pop nothing off the stack? It doesn't matter, like we just said, don't care what's on the stack, but legal, how do I write that? Or do I just have to exhaust the cases with like?
Yeah, generally exhaust the cases.
Look, network.
Sort of right here. And do.
Hey.
Go here now, yeah. We are going to reverse.
Well, if you push a dummy character and then read
So-
dummy characters, the stack that could potentially be. I mean, if you don't care what the character is.
Yeah, you add a character to the stack element that represents the wild card or
Right.
something like that.
It's just all.
Luckily, that is not useful in the slightest here.
So.
Yeah, so all these. It wasn't pushed. So you also need to push that, see.
So we see any. It's one, looks at. There's one here. It's things that it's. So it's gonna bring.
You have a bunch of different stacks at the same time.
You can only have one.
We're gonna talk about that.
There's
You can do this with a single stack.
Yeah, and then we'll carry, then we'll fail.
So. Then you'll also show this is the
And we'll talk about the theory of language classes that we could accept with other random data structures
So now
later as well.
again, this child's.
And why that question isn't anywhere near as interesting as you think it would be.
Well, it seems to me that if you, to go from a stack, like, I don't know this, like, what the actual theory is behind this, but it seems like the data structures have a sort of like order of complexity to them. And a stack and a tree must be like kind of the same in my mind.
Yeah, stack is a tree with
Yeah.
a single branching factor of 1.
Oh, okay. Well, and then but a graph, I feel like once you have a graph, like there's no way to make a more sophisticated data structures. Like that's the most sophisticated it could be, right?
Yeah, tree is just a graph with constraints.
Is a
character.
It's got the same.
So,
You can, once you have a graph, it's like, all right, we'll allow negative edge weights. We'll allow,
right, yeah, but it's like.
yeah, you can have multi edges in and out.
But a graph is a graph.
Mhm.
No matter how small.
How are we doing? Anyone want some more time to work on this? Or do you feel like we have
So I
a,
just
have an
like
answer?
the capital version of the stack characters.
Oh, that's
So I see name. I don't, whatever, I don't care.
Yeah.
I'll push that capital letter stack.
Yeah.
See what it
Kind
is.
of.
Yeah, then I have a bunch of no-offs to get to the second stage where I can guess if this is federal, if they're not those are good. Whatever better at into the.
Yeah, I think that was.
But I don't know what to do. Is, do I need the 2 more or the end of stack? Random string notation, would that fail? We could still do. And do I need 2 more here as well?
The question is, what do we want to use for our stack alphabet? We want to use zeros and ones again. We want to use the same character, A's and B's.
I did capital.
Capital A, capital B. Anyone else have a preference?
I used the exact same character. That's just me.
We use capitals. Why not?
I got the right idea.
This will be a bad idea eventually, once we start talking about using this to represent grammars and pushing aspects of grammars onto automata and vice versa. But for now, it's okay. Then we want an A on an A that pushes. We want an A on a B that pushes. We want the same things for B's. B on a Z gives us BZ. A B on an A, we're going to push a B on a B, we're going to push on. That's kind of gross.
See, it would be nice to just write like star, the whatever character.
Yeah.
Like just whatever it was, push it back.
Yeah, we do have to go through all the possible cases in an automata like this. But we need to guess where the middle of the string is. So this is one case where you can either think of this in terms of parallelism and just say we're going to fork a process every time we read a character. We're going to have one process continue to think that we're adding characters to the first half of the string, and one process that's going to start verifying that what we're about to see is every character that we have seen so far in reverse. You can think of it as guessing. Wherever the middle of the string happens to be, that's when we move from Q0 to Q1. But we need 2 different guesses. We need a guess on an A and a guess on a B. So an A, here it does not matter whether we are, if we want to be able to do this, see this plus saves us a little bit. So it can't be empty. If it were empty, then we'd have to worry about there being a Z here. So we can do an A with an A on the stack. Then just do a no op. We're just going to take off the A and keep it on. We need an A with a B on the stack, no op. We need a B with an A on the stack and a no op, and a B with the B on the stack, to the Noah. Annoying. Now we move to a Q1 where the goal is to see the exact characters in reverse. Question.
Why can't we just do a lambda on there? With both, like lambda A and lambda B, why is? that-
Yeah, I guess you could say on a character where it does not matter, because we don't want to move past this A or this B, do we? This should be lambda.
Yeah, because otherwise then the.
Yeah,
they're gonna have to
no,
be
that's a
done.
very good point. Very good point. All right, now we want to verify that everything that we are about to see is what we see in reverse. So to do that, we don't need quite as many for this. We just need to say, if we see an A, we need for there to be an A on the stack. So that we can pop it. If we see a B, we need there to be a B on top of the stack so we can pop it. If we don't see either of those characters, then this wasn't the reverse of that string, in which case that fork, that process is going to fail immediately. When we get to the empty string, we can transition for free. We read nothing. We pop the Z and push it back on, getting us to an accepting Q2. Where there's no transition. And again, if we weren't at the end of the string, we would fail because we're not at the end of the string. And there we have a multi-state NPDA. Where this state represents the first half of the string and the parsing of the first half of the string. This represents the parsing of the second half of the string. And then we have acceptance, the completion. I wish we had just a few more minutes because I kind of want to draw out a process tree for this, showing the different forks, even on a smaller example. But let's go ahead and do that with something that's fairly small, like A. And that way we don't have to worry about the different levels of transitions here, but this is the same forwards and backwards. So let's just kind of start a process tree here where we're in Q0, we read an A, there's nothing on the stack. So there's only one way for us to move forward, which is to push the A onto the stack. There's no Z transition here, so there's no alternate world we could be in. So we're going to put this capital A on the stack, move to here. As we move to here, there are now two things that we could do, and this is going to create a bit of a binary tree situation where we fork the process. One of them is going to say this second A is part of the left-hand side of the string. And the other is going to say the left-hand side of the string is over. Now we're in the verification part where we're going to look at, is this what came first? So if we do the first part of that, then we get a stack with a Z A in it. And if we go down here, we just get a Z and we're in Q1, here we're still in Q0. But regardless, we've read past this second A at the second depth of this process. So what happens from here is we would move over to Q2 because there's nothing really else for us to do. There's no A or B on the stack, so there's nothing we can do in Q1 except move to Q2. And not consume that. So this is going to fail because we're not at the end of the string. So this process just dies here. Continuing to this string, there are two things that we can do from here. We can either read this A and assume that it is part of the left-hand side, which is going to add a third A, or we pop off one of them and have moved to Q1. I guess technically this just moves us to Q1. This stays in Q0, and this process then does that pop. This one then branches as well, and we get 4 A's on the stack two A's on the stack, reading the fourth character, and this one has two branches where I guess there's not two branches, are there? We're not being empty, so this only has one path forward where we take this off, and this is the one that's going to be accepted. Both of these are gonna end up rejecting. Does thinking of this as kind of a tree help to understand the non-determinism? And if you're branching and doing all of this work at the same time and looking for a single path through this that accepts. Because we do make other branches, it's just that those other branches lead to failure for one reason or another. Either we reach the accepting state without having reached the end of the string, or we finish parsing the string and we are not in an accepting state yet. We're still processing the left-hand side of the string, and we missed the middle of the string. So we're still in that process, somewhere in Q0 or Q1 with the strings. All right, we'll come back to this tomorrow. And look at some more examples, but I'll have some office hours in an hour. Yep.
That.
Yeah, okay. I think what